All right, I'm the next speaker. If someone was late, my name is Piotr Sulkowski. I'm also one of the organizers. And just before I start talking about my lecture, one more announcement. We will take picture together just to have some recollection from the conference tomorrow, which is Tuesday, just before the lunch or just after the second morning talk. So this is like 1:10. So please just stay here after this lecture and don't run away too fast. Okay, and now the title of my series of lectures is Two-Dimensional Conformal Field Theory. Maybe it would be more proper to say quantum as well, but typically when people say 2D CFT, they already have in mind that they are talking about quantum theory. So this is the aim of my lectures, just to present it. It is indeed connected to what Tomasz was talking before and so on. I will not explain this connection that much, in fact. I mean, my aim here is just to present this part of the story in itself. It's in its own very interesting development, and in other lectures you will see the connection to celestial holography and so on. And what is important in this context is that these 2D conformal field theories are, as quantum theories, are solvable, in a sense that one can find amplitudes, in principle, all amplitudes in those theories. Of course, it is a bit subtle statement. In a given theory, sometimes it's still hard to find them explicitly, but at least in principle, there are ways to find them. So this is why this is important class of theories. And of course, they have vast applications from statistical physics to string theory, as you probably have heard of. So it's also important to understand their structure. And I will start also with some very basics. I'm not really sure how many of you already are familiar with these theories. Maybe some of you are not quite, so I will go slowly and from the basics. You can, of course, interrupt and ask questions. And I should also have mentioned in the website there is literature to all our courses. If you have not looked very carefully at the website, you can find various books or papers, articles in the website, and also for my course. But even though they are listed, then let me just comment very briefly on these positions that I listed. So one which is very important is how the story started, and it started with the paper by Beryavin, Polyakov, and Zamolodchikov. So this is often referred to simply as BPZ paper, and that was in nuclear physics in 1984. So this is not the only reason why this year was important for science, but one of important reasons. So for historical reasons, you can look at this paper. There is, on the other hand, maybe more introductory and explicit source, which is a book on CFT. Let me just write the acronym at this stage by Di Francesco Mathieu and Seneschal. This is a big yellow box, so you can easily find it in the library. And to some extent, my course will follow also what is in that book. And there are some shorter sources, lecture courses, also from some conferences or schools. One which is quite nice is by Ginspark. The title is Applied CFT. By Paul Ginspark. You can find it in archive. or by Cardy. This is more focused on statistical mechanics, but the basics are also nicely presented. And also a nice source, well, one of many nice sources is the book by Joseph Polczynski on string theory. This is quite concise and condensed, but still nicely presented. So if you would like to hear more or read more, you can look at these sources. And of course, in my course, I will not be able to provide all the proofs and so on. I will give many statements without proving them or arguing why they are correct, simply because there is not enough time. So probably you can find more details in these sources. All right. And well, to start with, I will recall some information about conformal group. And to start with, even though I'm supposed to talk about 2 dimensions, I will start with arbitrary dimension. So I will consider the dimensional space with metric G mu nu. And in general, under some change of coordinates, x to x prime, the metric transforms, well, in a way that we all should know. But I will also write some things maybe explicitly, which we all know, just to fix the notation. So let me write it. In this way. And then I will define a conformal group. As a subgroup of coordinate transformations, which leave the metric invariant up to a scale factor. So I mean that after one of these transformations, we get certain factor that I denote omega, and then the original metric. And these transformations preserve angles between vectors. So not necessarily the length of the vectors, but the angles between them. And it's also an important statement that Poincare group, namely translations and Lorentz transformations, are a subgroup of conformal group. And also, there is an important statement which I will not prove here, but you can try to do that. If you are in d dimensions in signature p, q, and for now, let's say that this is bigger than 2, then conformal group is isomorphic to SOP plus 1 Q plus 1. And this group has the following number of parameters. So in dimension d, this is d plus 1, d plus 2 divided by half. Which have the following interpretations. First of all, there are d translations. There is the expected number of rotations. Which we can write in the following way, and this is, of course, rotation matrix. So element of SOPQ. And there is one dilation or dilatation which scales the coordinates by a common factor. And finally, a very interesting class of transformations which are parameterized by some vectors, so there are d of them. And they are called special conformal transformations. Often you can find the acronym SCT for them to avoid this long name. But they are responsible by much of the structure that what I will be talking about. There is also a very interesting interplay between these dilations and special conformal transformations in quantum theory. There are various statements or theorems on various levels of rigor that in quantum world dilations imply also invariance under these transformations, but well, these are more advanced topics which I'm not sure if I will manage to reach. But for now, let me just write also how these special conformal transformations look like. They can be written in the following form, which at first sight might not be completely obvious what it means. However, it can be interpreted as a translation which is followed and preceded by the inversion. So this is also an exercise you can make for yourself. Where by inversion I mean operation which sends x mu to x mu over x squared. So this is important set of transformations that we will be considering. And what we will also use, it's a bit a matter of the notation, but well, we will need some objects. We will need so-called conformal invariants, namely some functions which are invariant under all these transformations. And in particular, there is a class of such invariants which are called cross ratios. These are functions of several variables. So, well, just let me write one example. If we have 4 points, then such a cross ratio looks like this. And one can also check, this is also a nice exercise, that for n points, there are n minus 3 divided by 2 independent cross ratios. Well, it's important to add that indeed there is such a number, but in sufficiently high dimension. By independent, I mean that they cannot be expressed through each other in some way. So in particular, in 2 dimensions, you might expect if you have 4 points, well, if you have 4 points, then there should be 2 such cross ratios, which indeed are independent for dimensions higher than 2, but in 2 dimensions, we will see that later. I'm not going to write the formulas now, but in 2 dimensions, in fact, you can express one through another. Okay, so this is one set of objects that we will use in what follows. And well, of course, at this stage, you might also write much more things. You might write infinitesimal form of these transformations and algebra they satisfy and so on, but I will skip that also for the sake of being able to say more maybe interesting informations later. Okay, so what I have said by now concerns just conformal transformations. However, what I'm going to talk about is not just transformations, but conformal field theory. So let me just give a few remarks concerning field theories or some objects which play an important role in those theories. And one very important object which we will consider in what follows is the energy momentum tensor. Which can be defined among others in the following way. If we know the action of the theory, it can be defined through some action, then the variation of the action with respect to the matrix is what we call energy momentum tensor. And it has various properties. I will just write down now one of these properties, which will be important in what follows. so this is the property which follows from the invariance.
Do you care about the difference between lower indices?
Well, in general, yes, but very soon I will just focus on 2 dimensions and Euclidean metric. So, but of course, oh, you mean?
There is no square root of determinant of the metric.
No.
Okay, so it's like density.
Sorry?
Okay, so it's tensor density then probably.
This is what? Sorry.
Tensor density.
In that sense, yeah. All right. So if we would like a scale transformation to be a symmetry of a theory, let me write it in this way. This would mean that the variation of the action should be equal to 0. So a simple argument is that we can write it in this way. So we essentially obtain integral of the trace, and from the standard argument it follows that the trace of energy momentum tensor should be 0. So this is important property which we will see plays a role also later. There are also certain subtleties with this statement in the quantum domain, but it's important to have in mind that at least classically energy momentum tensor should be traceless. Okay, so I should also stress that for the most of the lecture I will not be discussing some particular field theory. I will not write some Lagrangian or action or any other statement which, any other object which defines a given theory. I will be just trying to deduce what should be properties of theories which have conformal invariants in general. And I think in the last lecture I will give some examples of particular theories with such an invariance, but as long as possible I will try to not consider any particular theory. Okay, so even though I'm supposed to give 4 lectures, my time is really short. So I think what I wanted to say about conformal invariants and classical theories has just been said. And I will jump quickly to conformal invariance in quantum theory. Or in quantum field theory. And of course, one probably should say what is quantum field theory, which is a hard task. What I will have in mind, at least for some time, later on we will change the perspective a bit, but let us just think of a quantum theory as something that we obtain from doing path integrals. So we have some set of fields and some action or action functional, and there is something called partition function, which in principle should be obtained from such path integral. And also what we will be most of all interested in are correlation functions, which I will think of in the following way. We may have a number of fields depending on this coordinates axis. And then by the following expression, I would like to think of as the path integral with this form as well, but with those fields also under the integration. Okay, and now, well, this is just general notation of what we would like to see as the path integral, but let me try to define. Yes, this I wrote in the Euclidean notation, which we will be using in what follows. So by quantum CFT, I will understand a theory with the following properties, and in fact you can try to change the perspective a bit, and the properties I will write now you can try to think of as kind of axioms and then formalize it from another perspective. So the properties I like this theory to have is that it should have a number of fields. So by phi I will refer to as fields. And this may also include derivative of some fields. So sometimes it's important to have in mind that when I say field, it may be in fact a derivative of something, of some other field. And then there should be a subset of these fields, which are called quasi-primary. So that's an important name. Let me write these fields by curly phi. Let me just write it in this way. I just mean that they form a subset of all fields, which transform in some specific way under the conformal transformations, which I already mentioned. At this moment, probably you may already wonder why do I use this name quasi-primary and what does primary mean once I use quasi-primary. So, well, we will see later on what just primary means, but for now I define quasi-primary fields. Which transform under, and here I will write in a bracket just to stress this, under global conformal transformations. So the transformations I mentioned before are in fact global ones. We will see that in 2 dimensions there is a very important set of also local transformations. But for now we consider just these global ones. So if you have some transformation which takes x to x prime, then I'd like this quasi-primary fields phi I of x to transform simply with a scale prefactor. This is the Jacobian of this change of variables. And here is the exponent, which is an important number. This is delta I divided by a dimension of a space. So the convention is that we put this dimension d here in the denominator, and this delta I are called weights or dimensions or of a given field. That's right. Anyway, I think I can use this one, and then I will move to the left. Okay, so if this fields transform in this way, then one would expect up to some subtotals of, let's say, path integral, that expectation values should also transform with such a prefactor. And then that's the fields original one here. There are after the transformation. So this is one important property we will consider. And the next statement is that other fields, apart from quasi-primary, can be expressed through these quasi-primary fields. As linear combinations, possibly of derivatives. And finally, in the quantum theory, there should exist a vacuum state. Which is invariant under a conformal group. All right. So you might also wonder whether such theories exist at all, which have these properties, but it turns out they do. And as I say, if you don't like path integrals, you may just start with these properties and try to think of them as some kind of axioms. Okay, so this is what I will think of as quantum conformal field theory. And let me stress again, we will see that, at least in principle, this is indeed possible to find a way to compute all correlation functions understood in this way, in these theories. So that's why these theories are important. And it is also important that, well, apart from this property, there are certain properties of various amplitudes which follow just from conformal invariance. I mean, they follow just from the statement. If you now look at some specific amplitudes and specific types of conformal transformations, then you can restrict the form of various amplitudes of various multipoint correlation functions. So first of all, let me consider two-point function. Well, I will not derive these constraints in details. I may leave it more like an exercise. I will just give some intermediate steps. So first of all, you can think of how these functions should behave under rotations. Translations and special conformal transformations. So first of all, well, this is quite simple to deduce. If you would like to have invariance under translations of rotations, that you would expect that this correlation function should depend just on differences of this coordinates x1 and x2. And in addition, if you think of scaling transformations, if you like to have invariance under scaling, it means that you shouldn't have any length scale in your theorem. So in particular, correlation functions should not behave, for example, like exponents of something like this, but then if you have exponent or any other function which requires dimensionless argument, you would need to divide this by something of dimension of length. But you want to avoid that because of the scaling, which means that this function should be essentially some monomial of this quantity. And more precisely, if you look at more details how it behaves under scaling, you may conclude that it should it should have the following form. So these dimensions of these fields, delta 1, delta 2, should appear here. And it can be, well, proportional to, I mean, there can be some overall constant, which for a moment is not that important for us. In particular, let me stress here that scaling implies there should be no correlation then. So this statement is quite simple, a bit harder, but also interesting statement is that if you look at special conformal transformations, they imply that to have non-trivial amplitudes, these dimensions should be equal. So just to sum up, two-point functions have the following form. If we have two fields which have the same dimension, or they are just 0. Okay. I will still leave those places regarding our trip. So I don't know where should I move. Should I move to the right now? Okay, 2-point functions are still quite simple, but 3-point functions are a bit more interesting. So now I will also skip even these intermediate steps and just tell you how they should look like. And their structure is very important also for all other lectures. So it's important to write it explicitly. Here are some constants, which are, we will see why, also referred to as structure constants. If I denote by xij this quantity, then these 3-point functions must take the following form. And similarly, the fact that they depend on these differences between xi, xj, and not some function of those follows like before from invariance under rotations and translations, and that the scaling implies that you must have some monomials in these objects, and these exponents follow from other transformations. And let me stress again that I am still in any dimension. So you see that the form of 2-point functions or 3-point functions in conformal field theory is somehow fixed for quasi-primary fields. If you know what is dimension of these fields, if you know those deltas, that you don't have that much choice. Well, you may even normalize 2-point functions and somehow put this C1 to be 1, or include that in the convention for your expectation value. But then important quantities are this C1 to 3, which then are different in various theories, and to finding them is not that trivial task typically, but they give you much information about a given theory. And then finally, higher point amplitudes are not fixed like for 2 and 3-point functions. Well, I mean, they are partly fixed, but then they may depend on these cross ratios, which I mentioned before. Let me write x partly. So, for example, 4-point function must have the following form. There is some prefactor which is arbitrary function of cross ratios. And if you remember, I wrote how many independent cross ratios there are for n points. So there are 2, as I mentioned, at least for dimension higher than 2. If we have 4 points, so we cannot specify what this function is, but we know that it must depend on just such 2 arguments. And then there is some overall dependence on these coordinates x1 to x4, whose form is fixed. It is similar like before. There are also these differences xi, xj, and some exponent which is a function of dimensions of these fields. So this is the sum of these dimensions divided by 3. And I subtract delta I and delta j, where I and j are here in this product. So all that is in the exponent. So conformal invariance, at least one might think, does not fix this function f, and these basic transformations just leave this freedom. But what is very nice in this quantum conformal field theory is that, in fact, for much deeper reasons, it turns out that this is possible to fix what these functions are. And in a way, it also follows from conformal invariance, but not such a simple argument based just on these transformations, which I wrote before, but more elaborate transformations, which I mean, more subtle properties, which I will discuss in what follows.
What about positivity?
You mean of the amplitudes? Or
Yeah, I mean that we can construct expression from the fields which should be positive, and then amplitude of this expression should also be positive.
Well, I think it also translates, you mean the question of unitarity or presence of positivity, I mean positivity or negatively normed states in the theory. This is an important aspect. And in fact, there are theories which have states of negative norm, for example, which are still somehow consistent. But I will come to that on Wednesday, probably.
I have a question. In this 4-point function, this product of xij, shouldn't this be in the numerator, or it's just...
This is in numerator, and this exponent. It may happen that the whole exponent is negative, so...
Yeah, but the whole product, pi I less than j.
It's in numerator. Here is multiplication mark, so I don't write x because it will... yeah. But this is the rest of this line. Okay, so I have, well, around 10 minutes left.
So by the positivity, I meant that if we, for instance, if we consider some expression built from fields, which is positive, so like phi times phi double, then we would expect the amplitude of this expression, the expectation value, also to be positive. And this usually imposes very difficult to solve conditions on those point amplitudes.
Well, so these are not the conditions which are considered to restrict the form of correlation functions. And as I mean, these negative normed states, you can think of the normal state also as some kind of amplitude. And there are theories with states which have negative norms. So in that sense, they are allowed. And you do not need to impose unitarity in a theory for if you interpret it properly. So I'm not using this type of condition to restrict this form. Okay, so this form of these multi-point functions, which I just mentioned, is valid in any dimension. But let me now finally focus on 2 dimensions. So let's say that I already mentioned what conformal invariance is, what are conformal theories and quantum conformality field theories in any dimension. And now let me focus on 2 dimensions. Well, and I will also be a bit brief. So you can also make this exercise and see what transformations are allowed in 2 dimensions and what conditions are imposed by conformal invariance. And it turns out that imposes conditions which look like Cauchy-Riemann equations for functions which define transformations of the matrix. I mean Cauchy-Riemann equations from complex analysis. So then it follows that in 2D, in fact, conformal transformations coincide or can be identified with all holomorphic or analytic transformations. So if you use complex coordinates, then any holomorphic function of z and z bar is some particular conformal transformation. So this is important statement, and it's well, also good to look at details why it follows. So I also recommend this as an exercise, but it would take me a few other minutes, which I would like to just spend in other way. So if so, you can write a basis of infinitesimal transformations.
We treat F bar as an independent non-isomorphic function.
For now, this is just complex conjugate, but in fact, later on in quantum theory, we can think of z and z bar as independent ones. So simply sending z to z prime, which is z plus some monomial in z. Let me write it in this way. And similarly for z bar. Well, for all possible n's, so we also allow negative powers of z. So you can build all holomorphic transformations just from these ones, or analytic, well, just being careful what you mean by holomorphic or analytic. And for these transformations, you can write corresponding generators if you want to see how a given function or a field which involves these coordinates, how it transforms, then you can generate such transformations by the following operators. Well, by this again, I mean that if you have some field, then if you make some of these transformations, then you would like to see a change of certain field as written in the following form. And these ln's correspond, ln's bar correspond to those epsilons n or epsilon bar. Well, and this is, of course, simple to see. You would like to also have these powers of z, and then if you consider infinitesimal transformations, then to first order you see just derivatives of a given phi. So for that reason, if you look at some more details, these ln's look like this, and ln bars look like this. And you may see what commutation relations they satisfy. And these commutation relations form something which is called width algebra. And this is also a nice exercise. If you look at the commutator of ln and lm, you get n minus m with m plus n. The same for Barth generators. And else do not commute with L bars. So this is one of the reasons why in quantum theory you can think of this Barth and non-Barth quantities as independent ones, referring to this previous question. All right. Let me just stress that I didn't write such generators explicitly for general conformal transformations in any dimensions, but in 2 dimensions we will need them, so that's why I write them here. And what should I stress is also that not all of these LNs are well defined on the whole complex plane or on the conformal sphere. Just some of them, and those which are properly defined everywhere are referred to as global conformal transformations. And the other ones are not referred to as global. So those which are globally defined are those where this index n is 0 or plus minus 1. So in other words, we may say that the global conformal group is generated by L0 and L plus minus 1, and the same for L bars. And to have some idea what they are, let me just write explicitly. L minus 1 is just derivative with respect to z. So these generate translations, of course, just plain derivatives. Instead of thinking of just L0, it's a bit maybe more intuitive to think of L0 plus L0 bar, which is something like ZDZ, and the same for bar symbols, which you can write in the following way. So if I write Z in the standard radial coordinates, then this operation is a dilation in radial direction. And then such combination, L0 minus L0 bar times I, gives us rotations on the complex plane. And finally, L 1, which have this z square power here, they generate special conformal transformations. So this is infinitesimal form of these generators. And you can also write finite form of these transformations, and this is something which will already make a little contact with the previous lecture. Namely, in general, just this global subgroup gives transformations which can be written in the following way. For complex ABCD, and AD minus BC equal to 1. So this is, in other words, also transformations which form the group SL2C modded by Z2, where the Z2 follows from also invariance of changing the overall signs of ABCD. And this group is isomorphic to SO31, so this makes contact with the statement I made in the beginning that in any dimension, but in 2 dimensions just for global transformations, these conformal transformations are isomorphic to SOP plus 1Q plus 1. Okay, and the last remark is that physical states which arise in a given theory may be characterized by eigenvalues of these operators L0, L plus minus 1. And in particular, eigenstates of or eigenvalues of L0 are referred to as weights of some states. Well, L0 and L0 bar. So they are denoted by H and H bar. And there is a quantity referred to as scaling dimension. Often also denoted by delta. So this is the sum of H and H bar. And there is quantity referred to as spin, which is a difference of this. Okay, so I think that for now, this is all I can say, and I will continue tomorrow.
Are these weights the same weights as corresponding to Cartan algebra of conformal group? Or?
Yeah, in a sense, yes. Yeah. Yeah, as I said, When you look which transformations in 2 dimensions have this property that metric transforms just with a scale factor, and in 2 dimensions you find a condition which looks like Cauchy-Riemann equations, you know, from complex analysis. So any change of variables which is specified by some 2 parameters which satisfy Cauchy-Riemann equations gives this property that metric scales with overall factor. And for that reason you identify them with complex column.
But is there like an intuitive reason why 2 is special? Like, you know, is there like the terms that drop out in different numbers of dimensions, or like is there some intuition why 2 is special?
Well, I'm not sure if there is any better intuition than this one.
So if we consider this CF theorems on like in like some statistical mechanical context, for example, from lattice, is this scaling dimension going to be somehow related to the Hausdorff dimension of our theory?
Well, the scaling dimensions are identified with various exponents that arise in statistical physics.
All right.
So if you take some statistical model on a lattice and you take continuum limit, then you may identify that with various CFTs, and we will hopefully do that. For example, you can do that for Ising model. So then critical exponents can be expressed through these ways in some way.
Thanks.
Well, okay, it seems there are no more questions. And we should start the lecture. Well, I'm not sure how much time we need for a break. It should be starting now, but of course, we are a little late, so we should make a break. Do you want 10 minutes? 5 minutes? The question is what time